Welcome to the Deep Dive. Today, we're tackling a really intriguing question about large language models, LLMs, and specifically the role of reinforcement learning with verifiable rewards, or RLVR.
Right.
We all hear about models like OpenAI o1, DeepSeek R1, Kimi 1.5, making these big leaps in reasoning for things like math and coding.
Yeah, the hype is definitely there.
And the assumption is often that RLVR is the key, that it lets them self-improve, gain totally new reasoning skills beyond their initial training.
Yeah.
But what if that's not the whole story?
Exactly. The common narrative really paints RLVR as this engine of constant reasoning advancement. But this deep dive looks at a paper that really makes us stop and think, asking, does reinforcement learning really incentivize reasoning capacity in LLMs beyond the base model?
Okay.
And their findings? Well, they might just flip our understanding of how these models actually learn to reason.
And a big part of their investigation is how they measure this reasoning capacity, right? They're not just looking at, say, first try accuracy. They're pushing things using the pass at K metric with really large values of K.
Pass at K. So it essentially asks, if we give the model, say K, chances to solve a problem, does it manage to get it right at least once?
Okay.
And by using these really large K values, we're talking tens, maybe hundreds of tries, the researchers are trying to find the absolute boundary. What's the model capable of figuring out when pushed to its limit?
Across different kinds of problems.
Yeah, across challenging benchmarks, math, code generation, even visual reasoning. And they look at different LLM families, different RL algorithms, the whole works.
Yeah.
They want to see if RLVR truly expands this reasoning boundary.
And this is where it gets really interesting because the conclusions they reach are, quite surprising. They challenge that whole idea of RLVR constantly unlocking new reasoning powers.
Precisely. Their work suggests that RLVR might not actually be bringing out fundamentally new reasoning patterns. In fact, they found that while the RL-trained models often do better at first,
like pass at one.
Exactly, pass at one, they perform better initially. But if you really push the base models with loads of sampling, they often catch up. And sometimes they even overtake the RL-enhanced versions.
Wow.
Which suggests that maybe RLVR isn't expanding the potential reasoning scope as much as we thought. It might even, in some ways, be limiting it.
Okay, let's dig into this pass at K metric a bit more. We're so used to thinking about accuracy as, getting it right the first time. Why is looking at this boundary with large K so important for this study?
Well, standard metrics like pass at one, they give you a snapshot of, let's say, typical performance. But for really hard reasoning problems, a model might actually have the underlying ability to solve it, even if it doesn't immediately find the correct path. Pass at K with a large K helps uncover that hidden potential. It's asking, fundamentally, does the model possess the inherent capacity to reason its way to the answer if you give it enough shots to explore different ways?
So less about everyday efficiency, more about the ultimate ceiling of what it could figure out.
Exactly that. It's about finding the outer edge of its capabilities. And to make sure their pass at K numbers were solid, especially with those high K values, which can get noisy.
Right.
They used a clever, unbiased estimation method. So instead of just running exactly K samples, they generate more, maybe N samples, where N is bigger than K, and then use a formula to get a much more stable estimate of what pass at K would be, reduces the statistical wobble.
Okay, that makes sense. Now, with math problems, there's always that worry, isn't there, that with enough tries, a model might just, accidentally stumble on the right number without actually reasoning correctly, hacking the answer. How to deal with that?
Yeah, that's a critical point. They tackled it in two main ways. First, they filtered out problems that seemed easily guessable, where you could maybe get the number right without a proper chain of thought.
Okay.
Second, this is important, for a subset of the outputs on the harder problems, they actually went in and manually checked the chain of thought, the COT.
Human eyeballs on the reasoning.
Exactly. To verify that the correct answers really did come from sound logic, not just luck. And they did this for both the base models and the RL-trained ones.
And what did they find doing that?
Well, on data sets like GSM-8K and a filtered version of AME24, they found that the vast majority of correct answers, even at high K, were indeed backed up by valid reasoning steps.
Okay.
So that gave them confidence that pass it at K, even pushed high, was genuinely measuring the reasoning boundary, not just lucky guesses.
All right, so they've got this robust method for probing the limits. So let's get to the juicy part of findings. When they compared base models to the RL-trained ones on math problems, what did they actually see?
Across the board in mathematics, looking at models like Lame 3.18b, various sizes of the Quinn 2.5 family, comparing them to RLVR versions from places like Simple Zoo and Oat0 on all sorts of benchmarks, from GSM-8K up to really hard stuff like AME24.
Yeah.
The trend was incredibly consistent. At lower K values, pass it one, pass it few, the RL trained models generally did perform better, which, okay, that's what you'd expect RLVR to do, improve efficiency.
Sure.
However, as got significantly larger, into the tens or hundreds, the base models consistently started catching up. And then they actually surpassed the RL trained models in pass-at-K performance.
Wait, surpassed them. So the original model with enough tries was better than the one fine-tuned with RL.
Yes, better in terms of the breadth of problems it could eventually solve. There was this striking example on the Minerva benchmark with a 32 billion parameter model. At K128, the plain-based model actually beat the RL trained model by about 9 percentage points on pass-at-K.
9%, that's not trivial.
Not at all. It means the base model, just by sampling more, could unlock solutions to problems that the supposedly improved RL model couldn't reach.
So the potential was already there in the base model.
It strongly suggests that yes, the underlying reasoning capacity might be more inherent to the base model than we realize, and maybe RLVR, while making it faster to find some solutions, actually restricts the model from exploring other paths needed for harder problems when you give it enough time.
Uh-huh.
They even looked manually at some correct solutions from the base model on tough AME24 questions and found these really long, complex, reflective reasoning chains. Things it could do, just maybe not reliably on the first try.
Fascinating. And was this just one model family, or?
No, they saw it across different models and sizes, even with the Oat0 model on AME24, which started off way better with RL. The base model eventually caught up and overtook it at high K.
Okay, so a really consistent pattern in math. What about code generation? Did they see the same thing happening there?
Yep, remarkably similar pattern. They looked at Code R1, which is an RLVR trained model based on Qwen 2.57b Instruct 1M. They tested it on tough coding benchmarks like LiveCodeBench, Human Evil plus MBPP plus M.
Yeah.
And again, RLVR gave it a boost at pass at 1 better immediate performance, finding correct code faster. But as K increased, those gains from RLVR kind of flattened out.
Diminishing returns.
Exactly. And at larger K values, like K128 on LiveCodeBench, the base model again showed a higher pass at K. Its performance curve just kept climbing more steeply, suggesting it had more potential to solve more problems if you just kept sampling.
Wow. Math, coding. What about visual reasoning? That's another area of people using RLVR.
Same story there too. They used a system called EasyR1 to train Qwen 2.5 VL7b, a visual language model, on Geometry 3K. Then they evaluated it on filtered versions of MathVista and MathVision tests, specifically avoiding multiple choice to focus on reasoning.
And the result?
Mirrored what they saw in math and code. The base visual reasoning model demonstrated broader coverage, a wider range of solvable questions at high K compared to its RL-trained counterpart.
This consistency across domains, math, code, visual, is really compelling. It makes you seriously ask why. Why would RLVR, which is supposed to make models better at reasoning, actually seem to limit their ultimate potential boundary? The paper gets into possible explanations, right?
Absolutely. One of their central arguments is that the reasoning patterns you see in the RL-trained models, while they likely already exist within the base model's potential outputs, they just might be less probable initially.
How do they test that idea?
They use something called perplexity analysis.
Okay, break that down for us. What's perplexity in this context?
So think of perplexity as how surprised a language model is by a piece of text. Low perplexity means the model thinks the text is very predictable, very likely like something it might have generated itself. High perplexity means the text is more unexpected, more surprising to the model. So what the researchers did was take the correct reasoning answers generated by the RL-trained models, specifically on AAME24, and they fed those answers back into the base model and asked, how likely do you think these answers are? They measured the base model's perplexity for the RL model's outputs.
And what did that show?
They found that the perplexity distribution of the RL model's correct answers closely matched the lower perplexity part of the base model's own generated answers.
Whoa. So the base model wasn't seeing these enhanced reasoning steps from the RL model as alien or totally new.
Pretty much. It suggests these reasoning steps were already within the realm of things the base model considered plausible or even likely to generate itself, given the right nudge.
So the conclusion there is that RLVR isn't really inventing new ways to reason.
That seems to be the strong implication. It's not eliciting fundamentally novel reasoning paths. Instead, it's acting more like a very effective sampler, biasing the model towards those high-reward reasoning paths that were already present in its potential output distribution, just maybe buried a bit deeper or less probable initially.
So boosts sampling efficiency.
Massively improves sampling efficiency, yes. Makes it much more likely to find those good paths quickly, but, and this is the crucial bit, it seems to do this at the cost of exploration.
How so?
By heavily reinforcing those specific high-reward paths, the RL process might inadvertently discourage the model from exploring other, perhaps more winding but still valid reasoning approaches. This could lead to reduced output entropy, less variety in its thinking, and ultimately that narrower reasoning boundary we see at high K.
Right. It learns the best-known paths so well, it stops looking for others. That makes sense. The paper also brings in distillation as a comparison point, doesn't it? How does that fit in?
Yes, and that's a really important contrast. Distillation is different. That's where you train a smaller model to mimic a much larger, more capable teacher model, like learning from an expert.
Okay.
The study looked at a distilled model, DeepSeek R1 Distill Quinn 7B, and they found it consistently scored significantly higher on pass at K than both the original base Quinn model and the RL-trained version of that base model.
Ah, so distillation did push the boundary beyond the base model.
Exactly. The implication is that distillation can successfully introduce genuinely new reasoning patterns learned from the superior teacher model. This allows the distilled model to actually exceed the base model's inherent reasoning limits, which is something RLVR in these experiments didn't seem to achieve on its own.
That's a really key distinction. RLVR refines within the base's potential. Distillation can potentially add new potential learned from elsewhere.
Did they also look at whether the type of RL algorithm used made a difference?
They did. They used a framework called VRL to compare a bunch of popular RL algorithms: PPO, GRPO, Reinforce plus Ada, RLO, Remax, DAPO, quite a few.
And they introduced this neat metric called the sampling efficiency gap, or ESE. Basically, it's the difference between how well the RL model does right off the bat, pass at 1, and the ultimate potential the base model shows at very high sampling, pass at K256.
So how close does the RL get you to the base model's maximum potential with just one shot?
Kind of, yeah. It quantifies how far current RL methods are from optimally surfacing all the good reasoning already lurking in the base model.
And what was the verdict when comparing algorithms? Did one stand out as closing that gap?
Well, the striking thing was that while there were some variations, some algorithms might give a slightly better pass at 1, others might hold up a bit better at high K, the fundamental sampling efficiency gap remained consistently large, like over 40 points large, across all these different algorithms.
Wow, so none of them were getting close to perfectly efficient sampling.
Not even close, it seems. It suggests the limitation might be more fundamental to the RLVR approach in this context, rather than just needing a slightly better algorithm.
Any interesting quirks between the algorithms?
A few things, like DAPO sometimes got a higher pass at 1, but then dropped off more at K256, and it was computationally heavier. RLOO and Reinforce++ seemed pretty consistent across different K values. Remax actually performed a bit lower overall, maybe because of how it sets its reward baseline. But the big picture, that large efficiency gap was universal.
So it's not just which RL algorithm, it might be the RLVR mechanism itself. What about training longer? Does more RL training help, or does it hit a wall?
That's another thing they looked at, the asymptotic effects. They used GRPO and just kept training it for more steps.
More training equals better reasoning.
Well, yes and no. Pass at 1, the initial performance, did improve on the training data, as you'd expect. But the gains on test data, both similar stuff and out-of-domain problems, started becoming marginal pretty quickly, maybe after about 150 steps or so in their experiment.
Diminishing returns again.
Right. But here's the really critical part. Pass at 256, the measure of the ultimate reasoning boundary, actually started to decrease with more training steps.
Decrease. So more training made the boundary smaller.
It seemed to, yeah. The suggestion is that longer RL training might lead to overfitting to the specific high-reward path seen during training, making the model even less likely to explore, further narrowing its overall reasoning scope.
Okay, this is painting a really nuanced picture. RLVR is good for efficiency, maybe finding the obvious good paths faster, but doesn't seem to broaden the horizon and might even shrink it with too much training. What's the underlying reasons thought to be? You mentioned the base model earlier.
Yeah, the paper dives into the possible underlying factors. A key difference difference between RLVR for LLMs and, say, traditional RL, like in games, AlphaGo 0, DQN, is the starting point and the action space.
How so?
LLMs have this absolutely vast action space, all possible sequences of words. And crucially, RLVR doesn't start from scratch. It starts with a highly capable pre-trained base model. This base model acts as a prior.
Which is good, right? Gives it a head start.
It's a massive head start, yes. It helps guide initial exploration. But the researchers argue it might be a double-edged sword. Because the prior is so strong and the action space is so huge, the RL policy might really struggle to explore genuinely new reasoning patterns that lie far outside what the base model already knows.
Because going too far off the lead just leads to nonsense.
Exactly. Deviating too much likely results in incoherent text, negative rewards from the verifier, and the policy learns don't go there. Policy gradient algorithms, which are common in RLVR, naturally tend to reinforce responses that are already sort of aligned with the prior knowledge and happen to get a positive reward.
So it gets locked into refining variations of what it already knows.
It becomes very good at optimizing within the boundaries set by the pre-training, but finds it incredibly difficult to break out of those boundaries to discover fundamentally new ways of thinking.
Which leads us where? What's the path forward if RLVR isn't the magic bullet for expanding reasoning?
Well, the paper suggests that maybe starting RL from distilled models, which already have a better reasoning base thanks to the teacher, could be a temporary boost. But fundamentally, they think we might need entirely new approaches for exploration in these massive language spaces, or perhaps different training paradigms altogether beyond just applying standard RLVR on top of pre-trained models.
This has been an incredibly insightful deep dive into this paper. It really challenges some common assumptions. So to kind of wrap it up for everyone listening, the big takeaway seems to be that while RLVR is definitely effective at making LLMs more efficient at finding correct reasoning paths that likely already exist within them.
Right, boosting the pass at one.
It doesn't appear to be the mechanism that expands their fundamental reasoning capacity beyond the base model's inherent limits. And maybe counterintuitively, extensive training might even narrow that ultimate boundary.
That's the core message, yeah. It's a surprising finding because the narrative has so strongly been about RLVR enabling continuous self-improvement and novel abilities. This research suggests a different dynamic is at play.
And you highlighted that important contrast with distillation, which does seem to have the potential to introduce new knowledge from a teacher model and genuinely push that reasoning boundary outwards.
Exactly. It points towards needing a more diverse toolkit. Distillation offers one path for incorporating external knowledge, while RLVR seems better suited, perhaps, for refining and making existing capabilities more readily accessible.
It definitely leaves us with a really crucial question to think about. If RLVR is primarily about refining what's already there, rather than creating fundamentally new reasoning power, what are the most promising future directions for truly pushing the boundaries of LLM reasoning? Where do we go next to unlock that next level of intelligence?
A big question indeed.
Something for all of us to mull over. Thanks for joining us for this deep dive.